Hello, y'all. Welcome to lesson 135 of my DB chemistry curriculum. Today we're going over reactivity 3.2.9. This discusses functional groups and organic compounds may undergo oxidation. So we're going to come back a little bit to redox for the next couple videos. We will deduce equations to show the changes in functional groups during oxidation of primary and secondary alcohols, including the two-step reaction in the oxidation of primary alcohols. We will include explanations of the experimental setup for distillation and reflux. We will include the fact that tertiary alcohols are not oxidized, so we're just not going to cover tertiary, but we'll talk about why. And then we'll look at names and formulas of specific oxidizing agents, but those are not needed for the DP assessment. I will just lightly cover them as we get to that point. So the important functional groups we need to keep in mind for this unit are alcohols. As discussed, we're going to be looking at primary, secondary, not tertiary. Alcohol is ROH. We're going to be looking at ketones and also by extension aldehydes. So basically our carbonyls. So ketones are going to be R, C double bond O, R prime, and our aldehydes are just that, but at the end, R, C double bond O, H. Then we're also going to be looking at carboxylic acids. Carboxylic acids are R, C double bond O, single bond OH. Furthermore, we have to remember that alcohols can be primary, secondary, or tertiary, but we're going to discuss that. So that's going to be primary. Secondary might be R, C, R prime. And we're not going to cover tertiary, but again, we'll explain that in a little bit. Furthermore, we also need to remember oxidation. It was a bit ago, oxidation. But we can describe it in two ways. So oxidation we can describe as the addition of oxygen, but also the loss of hydrogen. You can also look at oxidation states of given elements in a molecule to determine whether it's being oxidized or reduced, but we're going to focus on these two things. With all this in our heads already, let's go ahead and look at an example of an alcohol, an aldehyde, and a carboxylic acid. So in this case, let's look at ethanol, ethanal, and ethanoic acid. So for all of these, they're going to be a carbon with three hydrogens followed by a carbon with something else going on. So ethanol has our primary alcohol, ethanal has our aldehyde, oops, and ethanoic acid has our carboxylic acid. So bringing in our idea of the addition of oxygen or the loss of hydrogen, we can start seeing what's happening when we look at our central carbon, or I guess that right carbon, or the thing overall. As we go from ethanol to ethanal, we are actually losing a hydrogen. And not just one, we are losing two hydrogens. And then as we move from ethanal to ethanoic acid, we are gaining one oxygen. So as we move from left to right, we can actually see that this is more oxidized and this side is less oxidized or more reduced. But right now we're looking at this in terms of oxidation. So what I'm going to do, and again, I'm going to do the cheat where I just copy and paste stuff, but I'm going to hold on to this for a minute. As we go through this unit, we're going to figure out how we go from one to the other. So starting with oxidation of primary alcohols. The way we do this is we use a suitable oxidizing agent. We'll commonly refer to this as just O in brackets. This will convert alcohol, and remember this is a primary alcohol, to aldehyde to carboxylic acids. So I'll go ahead and paste this back. If we were to use a little bit of chemical formula, we have our arrows to denote a reaction taking place, and we put that bracket O to say this is in the presence of an oxidizing agent. So I said I would mention a couple of them. So some good oxidizing agents. Some of the most common ones you'll see are potassium dichromate or also potassium permanganate. You may remember us using these when we were going over redox reactions because chromium and manganese in these will become incredibly reduced. Chromium goes from a 6 plus all the way down to a 2 plus. Permanganate comes from a 7 plus all the way down to a 2 plus. So they get reduced pretty heavily, meaning they're very good oxidizing agents. Furthermore, these will change color in presence of alcohol. And that's because they change their compound. So as they react with the alcohol here to oxidize it into an aldehyde and then to an carboxylic acid, we are changing the compound and thus they change color. Again, you don't need to memorize these, but it's good to know that these oxidizing agents will change color in presence of alcohol. Permanganate, or sorry, dichromate will change from like an orange to green, and permanganate will change from like a pinkish purple to colorless. And so you can tell that this oxidation reaction is taking place. So the problem is, you'll notice the oxidizing agent goes all the way to ethanoic acid. What if you want to stop at the aldehyde? How can we get that partial oxidation? Well, we can look at that. So a partial oxidation produces aldehyde. And the way we can do this is using excess alcohol. And that way, all the reactant will, the limiting reactant will be our oxidizing agent, meaning there won't be enough to continue the reaction. Furthermore, we can even use distillation can be used to remove the aldehyde. If you remember distillation, it's kind of like where you take your container and you run it through a condenser into our second flask. And this is done under heat. And what happens is it bubbles up and condenses into your flask. Now, this works because aldehydes have lower boiling points than alcohols and carboxylic acids. And one of the things you need to do is realize why that might be. I'm going to put this back here. So why does our aldehyde have the lowest boiling point? Well, remember, boiling point comes from intermolecular forces, and it looks like we have some hydrogen bonding here and here, but you'll notice in our aldehyde, we only have dipole-dipole. So this has H bonds, H bonds. And this only has dipole-dipole. Furthermore, if we're even looking at London dispersion forces, it also has the lowest amount of electrons, the lowest molar mass. So it's also going to have least London dispersion forces as well. So ethanol will very clearly be the first to vaporize. It has the highest volatility and therefore will be easily removed via distillation. So that's how we go ahead and get our aldehyde. Something you'll notice though is if we want to get our carboxylic acid, we often do this reaction under heat. Heat is really good at speeding up reactions. We've learned that in rate. We want to use heat so that we can uh, get that reaction to move faster, add more energy into the system, have more particles achieving energy greater than or equal to our activation energy if you're looking at a Maxwell-Boltzmann distribution. But the problem is our aldehyde leaves and therefore is no longer reacting with our oxidizing agent, which won't leave the solution. So how do we take that extra step into our carboxylic acid? How do we force that aldehyde back into solution to work with our oxidizing agent so that we can oxidize all the way to a carboxylic acid? Well, that's called heat under reflux. This is what we use to produce carboxylic acid. And basically, this is done with excess oxidizing agent because you want to make sure that you're not stopping at aldehyde. You don't want that partial where we use excess alcohol. And what we do, and I'll draw this out before I write it out, is we have our boiling flask. And then on top of our boiling flask, we put a reflux condenser. This is a spigot so that you can run water through it. Reflux, and we'll put a stopper at the top. Condenser. It may be better to look up an image. In fact, I could have easily imported one and I chose not to. And once again, we have our fire under it. And what the reflux condenser does is we recondense our aldehyde to force it back into the reaction chamber or reaction vessel, I might say. And so what happens is as your aldehyde bubbles up, it will condense, fall back down the walls, and continue to react in solution. So basically, you're heating this in a sealed chamber that has a condenser at the top to force that aldehyde back into solution. So that's how we go all the way to a carboxylic acid. So with that said, that is the oxidation of primary alcohols. Very briefly, we'll look at the oxidation of secondary alcohols. And this one is very, very simple. We only produce ketones. So if we look at it here, you'll notice there really isn't much else to do. We have, we have our carbon bonded to our other carbon chain and our alcohol. And when we oxidize it, well, we end up with RC double bond O R prime. And this is where we end. We can't really add another oxygen. Carbon can't form another bond. We have no hydrogens to take away from that carbon. So there's literally nowhere else to go. This is also why we don't oxidize tertiary alcohols. There's nothing to do from here. If we look at a tertiary alcohol, RC, R prime, R double prime, OH, we can't remove that hydrogen because then this will become an ion, which will be unstable and reactive, which will pull a hydrogen back. We can't add an oxygen because carbon can't have any more bonds here. We can't double bond because then that puts 5 bonds. So we cannot oxidize a tertiary alcohol. So our secondary alcohols go to ketone. Our primary alcohols go all the way to carboxylic acids. And that's it. I hope this helps you understand the oxidation of organic compounds a little bit better, and have a great day.